Okay, so today we're going to talk about some greedy algorithms. This is a new type of algorithm. Before we had discussed about like other kinds of algorithms, say dynamic programming. We talked about divide and conquer algorithms, right? So what is a greedy algorithm? So greedy algorithm is used to solve optimization problems. For most optimization problems, you want to find not just a solution, but the best solution. Suppose an optimization problem is, say, uh, traveling from Dallas to Houston, right? So you want to travel based on your criteria. You may want to travel the less number of miles, or you may want to save time, right? And there is not just one way to visit from Dallas to Austin, right? You can go in different ways. Say you can go to Austin, and then I think we take this way most of the time. Or even you can just take another route. You can go to, say, Louisiana, which is still away, right? And then from Louisiana, you can go to Houston. So when you're doing the optimization problem, this is also a solution, right? But probably we don't want this solution. We want the best solution. In this case, probably this is the best solution. So the greedy algorithm sometimes works well for optimization problems. It works in phases. That means and at each phase, you take the best you can get right now without the regard for future consequences. So when you are actually starting traveling from Dallas to Houston, you don't think the whole path. If you are being greedy, you will actually look for the suppose that best option that you have near hand. Say you have multiple cities and both of them go to Houston. Now you see that, okay, this is the best. Okay, so you take this and you take about the rest later. So once you go to the second point, then you will again uh, choose you're being greedy, so you go to the next step and then you think again. So you hope that by choosing a local optimum at each step, you will end up at a global optimum. Okay, so you take the best decision here, then you go here, and then you try to, there are like different options here as well, right? So you go there and try to take the best decision there, right? And you hope that through this, the whole thing is going to be optimized, right? Suppose one example is you have certain amount of money and you want to change that money with the fewest possible bills and coins. Say someone gave you like 639, uh, you have to return 639 dollars to someone. So you want to give him the lowest possible amount of number of bills. So what you try to do is to minimize the number of bills. You try to give him the bill that is the nearest to 639. That's obviously a $5 bill, right? You are trying to be like optimize it. Like you are not thinking about the whole thing, what's going to happen later. For now, you think, okay, if I give him a $5 bill, I'm covering most of it. Okay. Next, my next greedy choice is I have like $1.39 left, right? So why don't I give him another $1? That way I have like 39 cents left. Okay, so now the best choice is give him the 25 cents coin, right? Now we have 0.14. So give him a dime. Now we have 4 cents. And now give him 4 1-cent coins, right? Okay, so in total, you just use 1, 2, 3, 4, 8. 8 coins, or you are using 8 coins or bills. Okay. For US money, the greedy algorithm always gives the optimum solution. Here is the issue. Like in the greedy algorithm, sometimes it's challenging to get the optimum solution. So suppose here's a fictional monetary system, say they name it crowns. Suppose you have 1 crown bill, 7 crown bill, and 10 crown bill. Now you want to do the same thing to return a change of 15 crowns. So what do you think? So 15 crowns. Then you think, okay, so I want to optimize. I want to give like return the change with the least number of bills. So why don't I use 10 crowns, right? If I use 10 crowns, then 5 crowns is left. So next, use 5 1 crowns, right? So in total, how many bills I'm using? 6. 1 10 crown and 5 1 crown. That is 6. But you see, although this is a solution, but this is not the most optimal solution, because instead of using this, if I could just use 2 7 crown bills and 1 1 crown bill, in that case 1 crown would have left, right? And then 1 crown bill, then I could just do it using 3 bills, right? So here is one issue of the greedy algorithm, that being greedy is not always the optimal. Okay. So let's talk about a scheduling problem. So you have to run 9 jobs. 9 jobs, or say these jobs might be, say, downloading something from the web, and the running times are this. You have 3 processors or 3 computers that can run these jobs, and you want to do all these downloads as fast as possible. What's your plan? What algorithm you are going to follow? So it's very intuitive that we probably want to do it, give them the parallel tasks. So probably I would like to divide the task between these 3 computers or processors equally, right? I want to divide so if I can divide them equally, right, the whole thing would be the fastest. So my strategy might be that I start giving the largest tasks. So I get the first 3 largest tasks and give it to the 3 processors, right? Okay. Yeah. So I'm trying to just do as much parallel work as possible. So I'm just giving the largest task divided into the 3 processors. Okay. So then this is done, right? After 15 minutes, this is done. So I give it, using the same strategy, I give it the next large task, and then this and this, and finally this is what happens. And the time to complete the whole 3 tasks is this, right? This is 35 minutes. Okay, let's try it in a different strategy. So this is a solution, but let's see if we can do even better. So this is a greedy solution. Let's look at another greedy solution. This time I am thinking, okay, I want the computers to download as fast as possible, but I want to divide the tasks evenly between them. So why don't I start with the smaller files, smaller tasks? So I give the first computer to download the file that takes 3 minutes, the second one 5 minutes, and third one 6 minutes. Okay, so after 3 minutes, this is going to be done. So I will give it the next smallest one, so the 10-minute task. I will give it the 10-minute task, 11-minute task, and 14-minute task. Okay, so next this is done, right? So this one gets the 15-minute task, this one gets the 18-minute task, and this one gets the 20-minute task. Now in total, you see that I need like 40 minutes to solve the problem, right? I am still being greedy. Like, greedy means I am just trying to optimize as much as possible, uh, being in a greedy fashion. But you see, this greedy choice is even worse than the first thing that we did, right? But still, it's a solution. Okay, so what is the optimum solution? So the best solution was, like, if I could do it this way, that way, I could uh, try all possible works in 34 minutes. So this is the proper solution. But the problem here is, how do I know like this is a proper, how to find this proper solution? I could just take all combinations, say we had these tasks, right? So we had all these tasks. So I could just break them down. Okay, let's see randomly 3, 10, and 14 goes to the first computer, and then 11, 15, 18 goes to the second computer. I could just make different combinations, right? And try to see which combination is the best. But that would have been like an exponential algorithm. Okay, we know that not all greedy algorithms will give you the optimal solution. So we don't want to think much about this. We want to talk about some classic greedy algorithms that actually work like magic. They give you the nicest optimal solution. Okay, so three of those algorithms we will be talking about. So these two, the final two, actually solve the same problem. So for the first greedy algorithm that we are going to discuss today is the Dijestra's algorithm. This is for finding the shortest path in a graph. We already know what a graph is. And then the last two algorithms are for finding a minimum cost spanning tree. So both of these are like from minimum cost spanning tree. And these are like two different algorithms, but they solve the same problem. So we'll discuss all these three algorithms.